We need to obtain the value of 1 plus iota times square root of 3 raised to the power of 8 plus 1 minus iota times square root of 3 raised to the power of 8. So let's begin by first considering our complex number 1 plus I times square root of 3 as z1. We have z1 given by 1 plus iota times square root of 3, and we will consider our second complex number 1 minus iota times square root of 3 as equivalent to z2. We want to convert the given complex number to its polar form. So that means we will need to find out the value of r1 and theta 1. So r1 will be simply equals to square root of 1 squared plus square root of 3 squared, which is going to give us the value 2. And theta 1, which is the argument of our complex number z1, that's simply the inverse tangent of the imaginary part divided by the real part. So this is going to give us tangent inverse of tangent of pi over 3, because we know that square root of 3 is tangent of pi over 3, such that theta 1 gives us the value pi over 3. Now we can represent our complex number z1 in the polar form as 2 multiplied to cosine of pi over 3 plus iota times sine pi over 3. Now coming to the second complex number z2, so here our r2 value will be equals to, so underneath the square root, we'll take the real part, square it, and add it to the square of the imaginary part, which is also going to give us the value 2. And theta 2 is going to be equals to the inverse tangent of the imaginary part, which is negative square root of 3 divided by the real part, which is 1, which will be equals to tangent inverse of negative times tangent of pi over 3. Now tangent is an odd function, so since it's an odd function, we can also represent it as tangent of negative pi over 3, which is going to give us the value negative pi over 3. So this is the value of our argument of the complex number z2. So z2 in its polar form will be 2 times cosine of negative pi over 3, but cosine is a even function, so we'll simply get cosine of pi over 3, whereas sine is a odd function, so we'll get negative iota times sine pi over 3. Fine. So let's label this as number 1 and this as number 2. Now what we'll do, we'll raise z1 to the power of 8. The z1 raised to the power of 8 is simply 2 raised to the power of 8 multiplied to cosine of pi over 3 plus iota times sine pi over 3 raised to the power of 8. And z2, we are also going to raise it to the power of 8. So we have 2 raised to the power of 8 multiplied to cosine of pi over 3 minus iota times sine pi over 3 whole raised to the power of 8. Now we'll be using the De Moivre's theorem, which simply states that whenever we have cosine of theta plus iota times sine theta raised to the power of n, this will be equals to cosine of n theta plus iota times sine of n theta. Now this works for negative values as well. So therefore, our complex number z1 will now become z1 raised to the power of 8 will now become 2 raised to the power of 8 multiplied to cosine. So we are going to multiply 8 to the argument of both cosine and sine here. This is going to give us 8 pi over 3 plus iota times sine 8 pi over 3. And then our complex number z2 raised to the power of 8 can be represented as 2 raised to the power of 8 multiplied to cosine of 8 pi over 3 minus iota times sine 8 pi over 3. So let's label each of them as equation number 3 and 4. Now we're going to add equation number 3 and equation number 4 together. So this is going to give us z1 raised to the power of 8 plus z2 raised to the power of 8. So this will be equals to 2 raised to the power of 8 multiplied to 2 times cosine of 8 pi over 3. Because the imaginary parts are additive inverses of each other, so only we have 2 real parts. So that's giving us the factor 2, which combined with 2 raised to the power of 8 to give us 2 raised to the power of 9 times cosine of 8 pi over 3. So let's work around 8 pi over 3. So we have 8 pi over 3. This can be also represented as 9 pi minus pi over 3, which means we have 9 pi over 3 giving us 3 pi minus pi over 3. And now 3 pi can be also represented as 6 times pi over 2 minus pi over 3. So here we have now cosine 8 pi over 3. This can be represented as 6 times pi over 2 minus pi over 3. Now 6 times pi over 2 means we have an even multiple of pi over 2. So cosine will remain as a cosine function. So we'll have cosine of pi over 3. Now we have to check in which quadrant the argument of this cosine function lies. Fine, so let's do that. So here in argand plane, so we have 1 pi over 2 in the first quadrant, 2 pi over 2, 3 pi over 2, 4 pi over 2, 5 pi over 2, and 6 pi over 2. So that means we are in the second quadrant. However, we are also subtracting pi over 3 from 6 pi over 2. But since pi over 3 is less than 90 degrees or less than pi over 2 radians, we can say we are still in the second quadrant where the sine function is positive. That means everything else is negative. So we are going to get negative cosine pi over 3. So this is now multiplied to 2 raised to the power of 9. So we have 2 raised to the power of 9 and cosine of pi over 3. So that's half. So we have negative half, or this value simply equals to negative 2 raised to the power of 8. So negative 2 raised to the power of 8. So our value is negative 256.